A paperclip slides toward a magnet, and the strange part is not the paperclip. It is the air in between. Nothing visible touches either object, yet the space suddenly behaves as if it has picked a side. That is why magnets feel like magic. The honest answer is better than magic, and it is hiding in that gap. Not in the magnet, not in the paperclip, in the empty space between them, where it looks like nothing at all is going on. So what actually changed between the magnet and the paperclip? Start with the feeling that bothers people most. A magnet seems to reach across a gap and grab something. On a white table, it can pull a paperclip, swing a needle, or make another magnet twist in your fingers before the two ever meet. We are used to pushes and pulls that arrive through contact. A hand pushes a cup. A string pulls a weight. Here, the empty space seems to do the work. That is the first illusion to fix. The space is no longer doing nothing. This is the idea behind a magnetic field. The magnet changes the region around it so other objects can feel a force there. No invisible wires are hanging in the room. Field lines are a picture, not a glowing structure you could see with your eyes. The picture still matters, because it gives shape to the force. Close to the magnet, the effect is stronger. Turn the magnet around, and the directions change. Bring in a second magnet, and its orientation suddenly matters. Attraction is only half the story. Repulsion matters just as much. If all magnets ever did was stick to things, you could still imagine a hidden hand reaching out to grab. But when like poles push each other away, the force stops looking like a one-purpose grabber and starts looking rule-bound. Something about the space has become organized. It rewards some positions and rejects others. Picture a hill you cannot see until a marble starts rolling across it. Before the marble moves, the surface looks flat. Once it moves, you realize the landscape had shape all along. A magnetic field is like that. The paperclip does not move because the magnet cheated. It moves because the landscape around the magnet is no longer neutral. That also explains why the poles matter without turning the idea into a school poster. North and south are not magic labels. They are a compact way of saying the field around the magnet has direction. Flip one magnet, and the whole force map between the two objects changes. Opposite poles settle together. Like poles refuse. What matters here is not the vocabulary, but the proof that the invisible force has structure. Once that lands, the question gets sharper. If a magnet is changing the space around itself, why does that change matter so much to a paperclip, and so little to the table, the glass, or your sleeve sitting right beside it? This is where everyday experience quietly misleads people. We learn very early that magnets pull metal. It sounds practical. It is also sloppy enough to cause trouble the moment you look closely. Metals do not all answer a magnet the same way. A paperclip made from the right kind of steel responds fast. Iron does too. Nickel and cobalt belong in that same everyday family. But plenty of objects people casually call metal do not leap toward a fridge magnet at all. The force is selective. That is the second reason magnets feel uncanny. The invisible pull does not spread out like a general command to everything shiny. It seems to choose. That choice is the real clue. Take the paperclip chain. One paperclip hangs from the magnet. A second one hangs from the first, then another. For a moment it looks as if the magnet has made brand new magnets out of plain office supplies. A beautiful little fake miracle. What you are seeing is temporary magnetization. The field from the magnet nudges tiny magnetic contributions inside the paperclip into a more organized pattern, and the paperclip begins answering the field strongly enough to influence the next one. The force looks contagious. What is really spreading is alignment through a material that can support it. That is why the trick partly fades when the chain comes apart. The paperclip never became the same kind of permanent magnet as the original object. It borrowed order. While the field was there, many tiny contributions inside the metal were coaxed to face a similar direction. Remove the strong organizing influence, and much of that order relaxes. This beats saying magnets simply like certain things. Liking explains nothing. A material either has an internal structure that can be lined up into strong visible magnetism, or it does not. The difference lives inside the material, not in some mood the magnet feels toward it. That also guards against another common mistake. A non-magnetic material is not dead or featureless. The safer idea is that most everyday materials just do not line up into strong human-scale magnetism the way iron-rich materials can. Their tiny magnetic effects tend to cancel, stay weak, or fail to organize in any lasting way. So the magnet is not shouting at the universe and getting ignored by most of it. It is offering a force that only certain structures can answer dramatically. By now, the shape of the puzzle has changed. We are no longer asking why the magnet reaches out. We are asking why some materials are ready to answer back. Here is the deepest part of the story, and it only works if we keep it visual. Inside a ferromagnetic material, picture many tiny regions acting like little arrows. Not literal painted arrows, of course. It is the image that helps us see the behavior. In most ordinary pieces of material, those little directional contributions point all over the place. One way here, another there. Add them across the whole object, and much of the effect cancels out. That cancellation is the normal state. Strong visible magnetism is the special case. The key idea is the magnetic domain. A domain is a region where many of those tiny contributions line up together. If different domains point in different directions, the object as a whole may still not look very magnetic from the outside. But once enough domains swing into the same direction, their effects add instead of cancel. The whole object develops a strong overall north-south structure. Now it behaves like a real magnet at the scale our hands can notice. This is why the paperclip chain mattered. It hinted that the material could be organized. Think of domains as neighborhoods of agreement. In one neighborhood, the tiny arrows vote east. In another, they vote west. While the votes stay split, the object keeps a low profile. Once many neighborhoods begin agreeing, the profile changes completely. What looked inert now carries a strong outside field, because huge numbers of tiny magnetic contributions have stopped canceling each other. That is the trick at the heart of a permanent magnet. No heroic particle, no secret force gland hidden in the object. The work is collective. It also explains the difference between a permanent magnet and a temporarily magnetized object. In a permanent magnet, the internal alignment holds stubbornly enough that the object keeps its organized state. In a paperclip, an outside field can push the internal pattern into better order for a while, but much of that order drains away when the organizing field leaves. Same logic. Different stability. Electrons are fine to mention here, but only after the domain picture is already doing the heavy lifting. Educational sources often describe electrons as tiny magnets, and that works as a bounded simplification. The danger comes when the explanation jumps straight from paperclip to quantum weirdness and leaves no clear picture to hold onto. Domains are the bridge that keeps the story physical. Once you see that, magnets stop looking like rare enchanted stones and start looking like materials whose internal votes have been forced into agreement. And that opens the next leap. Magnetism is not only something stored inside a special chunk of metal. Under the right conditions, you can build the same kind of field from electricity. Here the whole topic gets bigger. Take an ordinary wire. Nothing about it looks like a bar magnet. It is just a path for charge to move through. But when electric current flows, the space around that wire changes. A magnetic field appears around it. The striking part is the shape. The field does not point away in one straight blast. It wraps around the wire in circles. That detail matters because it proves magnetism is not trapped inside permanent magnets. Moving charge creates the same kind of invisible force map. Reverse the current, and the field reverses with it. So the effect is controllable. It has direction. It answers rules. Engineers are no longer stuck finding magnets in nature or manufacturing them once and living with the result. They can command the field by commanding the current. Now take the straight wire and wrap it into loops. This is the clean route to a solenoid, and the visual payoff is excellent. Each loop creates its own circular magnetic field. When the loops stack in the same arrangement, those effects pile up. The field becomes more concentrated and starts behaving much more like the field around a familiar magnet. The same basic force that looked spread out around a straight wire becomes gathered and useful. So the story has quietly unified itself. Permanent magnets work because internal alignment creates a strong organized field. A current-carrying wire works because moving charge creates a field. A coil works because many small field contributions are arranged to reinforce each other. Every time, what matters is the force pattern in space, not the object label. That is why electromagnets feel so satisfying. They are the moment magnetism becomes something you can manufacture on demand. Turn the current on, and the field appears. Change the current, and the field changes. Pack the wire into loops, and the effect strengthens. Electricity has just built magnet behavior from scratch. It keeps the story out of classroom unit mode too. We do not need every law and mnemonic. We need one durable mental image. Charge moves, the space around it gains structure, and clever arrangement lets many small effects add into one strong, useful field. Once that clicks, the opening paperclip no longer looks like an isolated trick. It is the smallest member of a much larger family. The same no-touch force can now be generated, steered, reversed, and put to work. The best everyday proof of that is a motor. At first glance, a motor hides the same contradiction we started with. Parts separated by a narrow air gap still manage to create motion. A rotor turns, a stator stays fixed, current flows through one part of the machine, magnetic fields interact across the gap, and mechanical work appears. The scale is larger and the hardware more serious, but the strange feeling is identical to the paperclip crossing empty space. Something important is happening where nothing seems to touch. That air gap is the callback that makes the whole episode cohere. A motor works because magnetic pushes and pulls can be timed. One attraction on its own would only produce a tug, one repulsion would only produce a shove. But if the current changes in the right sequence, the machine keeps creating the next push at the right moment. The force stops acting as a single dramatic event and becomes choreography. That is a real shift in the story. Magnets stop being desk toys the moment the force can be sequenced, repeated, and controlled well enough to spin machinery. The invisible field is no longer only a surprise, it is infrastructure. And notice what did not change. The machine still relies on space being altered. The rotor does not need to scrape or hook itself around the stator to know which way to move next. The field provides the instructions through the gap. It tells the moving part where the next energetic downhill path is. That is why the motor matters here. It proves the opening mystery was never small. It also shows why control matters more than spectacle. A good motor impresses not because magnets are dramatic, but because a field can be created, reversed, strengthened, and timed with precision. The useful magic is not that the force exists, it is that the force can be disciplined. Once you have that, huge parts of modern technology stop looking like piles of separate inventions. They start to look like variations on one theme. Create the right field, arrange the right materials, put the timing where it needs to be. Then let the invisible geometry do work that would otherwise require gears, friction, or direct contact. So by the time the motor spins, the title has changed meaning. We started with why magnets feel like magic. Now the answer is almost the opposite. They feel magical because we are watching a real physical rule do something so cleanly that it barely advertises the mechanism at all. And if a controlled field can spin a machine, the final step is not hard to guess. The same logic scales far beyond a workbench. One powerful example looks inward, another looks outward. MRI uses very strong magnets to organize matter inside the body. More precisely, the magnetic field helps align protons, and the system reads what happens as they relax back. That is a very different job from pulling a paperclip. But the family resemblance holds. A magnetic field is imposing order. Matter is answering that order in a measurable way. The machine turns that response into information. That is one reason MRI feels like such a prestige example. It proves magnetism is not only about dragging metal around. A strong field can quietly organize the tiny physical behavior of tissue deeply enough to reveal structure inside a living person. The other example is maglev. Here the force is asked to do something huge and visible. Magnetic attraction and repulsion can lift, stabilize, and help propel a train. Again, the specific engineering details vary, and the hardware can become extremely advanced. But the core idea stays simple. The no-touch push and pull from the opening scene has been scaled until a vehicle can ride on it. That is the right way to use applications in this story. Not a pile of cool facts, and not a victory lap detached from the mechanism. MRI and maglev are bounded consequences. They show what happens when the same field logic meets different materials, different goals, and different scales. By this point, the title promise has been paid off. Magnets feel magical because they make space behave actively. They feel selective because only some materials are built to answer strongly. Permanent magnets work because domains line up instead of canceling out. Electromagnets work because moving charge creates a field, and coils let many small effects reinforce one another. Motors, scanners, and levitating trains are not side quests. They are what happens when that same hidden grammar is pushed into useful forms. The better explanation does not flatten the wonder, it sharpens it. The paperclip on the table, the aligned domains inside a magnet, the wrapped wire in a coil, the rotor turning through an air gap, the body inside an MRI bore, the train riding above its guideway. 6 versions of one invisible pattern, repeating at different scales. That is why magnets still deserve to feel weird. The world really does contain forces that can shape action across empty space. The achievement of science is not to make that less strange. It is to show exactly how the strangeness is built. Go back to the paperclip crossing the gap. At the start, it looked as if the magnet had cheated and the air had suddenly started helping. The scene reads differently now. The space was never empty in the way it first appeared. The magnet had given it shape. The paperclip was made of a material able to answer that shape. And once electricity enters the story, we can build, steer, and scale the same force until it runs motors, MRI systems, and maglev lines. So magnets do not stop feeling magical once you understand them. They feel magical for a better reason. They reveal that empty-looking space can carry structure, and that matter can answer that structure by rules precise enough to build a civilization on.